Okay. Good afternoon, all. So I guess yesterday you have class from Dr. Rashpat Babu, and I heard from him what he covered. So today's session I will be primarily covering a few parts of what I covered in my last lecture. That was lecture two, as well as where he ended. I think he covered the Deutsch-Jox algorithm and give you a brief like mathematical circuit or the oracle and what is an ancilla qubits and all those descriptions he had covered. So post that we will also start with a few parts of quantum algorithms. We'll maybe we will be watching another algorithm, a full-fledged version of that. And we will also look into theoretically at least some of the quantum algorithmic paradigms, which means like we have our dynamic greedy backtracking. Similarly, what are all the generic techniques that we have for the quantum version? So this is all something that I have planned for today. And with that note, let us start. So initially, quantum algorithm, if you know that what is an algorithm? So it's basically some recipe in very easy word, where with respect to computation we believe that algorithm is a process which has some input and some output, where number of inputs is definitely or it can be like a greater equals to zero. That is, we can also design or devise an algorithm with no input, but the number of algorithms should be exactly uh, it cannot be exactly zero, so it has to be at least one. So number of outputs can be greater equals to 1. So this is a generic definition of an algorithm, right? And what does an algorithm solve? There is a problem. With respect to that, we devise some algorithm which can solve the problem for a specific input instances. That is the definition. Now, why we are heading towards quantum algorithms is because from our very like first class, we have seen that we are just trying to get some solutions for a specific set of problems, not for very easy problems, but for some specific set of problems, we try to come out with some better solution. Now, that better can be either at least in terms of lesser number of queries, which we refer as a quantum advantage, or it can be literally significantly doing some like improvement, which is kind of a quantum supremacy, where it might differ exponentially with respect to the complexity or computational complexity. For example, if in classical we can solve something in 2 to the power n, and if we can find some quantum version of the same problem which can solve it in n, then we call it as a supremacy. So this, just look into the last line. So the machines using quantum processors or quantum processors might be able to perform computations that classical computers can only perform very poorly. So just focus on this word, that might be able to. So definitely what we want is, or aim for, is some sort of advantage. And finding and like obtaining some supremacy is beyond better, right? So, and this is again just to let you be motivated that why we need some quantum algorithm is because of the Shor's algorithm. I already mentioned it, that the best classical version with for a 300 digit number, if we have to find its prime factors, is going to take 10 to the power 24 steps and 1,50,000 number of years on a terahertz computer, right? That is 10 to the power 12. On the contrary, on Shor's algorithm, it will take 10 to the power 10 steps. And similar capacity type quantum computer of the terahertz capacity, 10 to the power 12 cycles per second, can solve it in less than 1 second. So just see that what we are actually looking into. or why are we, as a researcher, we can be motivated to devise some quantum algorithm, right? So the implications is definitely we want something that should break, or that should actually solve or make the NP-hard problems easy. That is our aim. So we all are aiming towards that. Okay, and there is a security aspect as well, where we mentioned that at least the man in the middle attack, we don't want that to happen, right? So in details of this man in the middle attack and the security aspect, we will be covering in quantum communication, a part of it. It's a part of cryptography. So when we will be covering that, we will have a deeper dive into. So two kind of things are there. One is a betterment. In non-tech term, we call it as an optimization, or finding optimal solution, best or optimal at least. Optimal means either our quantum is better in terms of cost, or it is better in terms of like efficiency, or it is better in terms of say what is that, speed up and all. So likewise, or it is very time saving. So this is all what we refer as an optimal solution. So we have to find the best one. Another very important aspect is we have to totally secure our solution. So security is another very important aspect, right? So security is another very important aspect. And the problems that only rely on these kind of thing, let me just give you. There are basically the major versions that we have is quantum AI ML, quantum optimization, simulation or quantum simulation, and also I'm just marking broadly depending on the requirements of the problem. Now definitely quantum chemistry, quantum, a lot of such like material discovery, all these things are there. Just in a broader sense, with respect to computing, I'm just writing. Another very important one is like cryptography or security. So for security, we are very much in threat because of the evolution of quantum computers. But for quantum AI ML, we head towards that finding maybe say better eta. We want more efficient solution, right? Or say for example the case of say principal component analysis, where we actually are unable to feed all the columns or all the specific features or properties, and we try to find through some of the techniques, diagonalization and all those techniques, whether what are the major components that can significantly imply our decision making or kind of our solution that we are aiming towards. So in these kind of problems, where we actually we want an unbiased solution or an efficient solution, we mostly talk about this particular field called quantum AI ML. And for quantum optimization, it is, say, for example, cost we have to say minimize. We have to check for time. Time should be also minimized. And say, mm, approximately better solution. So better in terms of the same thing. Say, yeah, primarily I think cost and time. You can like broadly map it into these two, because otherwise efficiency and all. So I'm not saying that quantum optimization problems they do not want to increase the efficiency, but of course they want it. But mostly it has to be very quantized. So that's why we want to literally understand that how better it can be like. So of course it is some way inclined towards a classical AIML, what we measure in the classical AIML as the benchmark metrics. Similarly for the classical optimization, what we measure at the benchmark metrics. So we will be following both the things. And for simulation, it is not simulating something, say a quantum phenomena in a classical computer. Rather, it is bit reverse. It is that a few of the such particles or some natural phenomena is there in nature, which is very difficult to be simulated on a classical computer. So for those kind of algorithms, we need a quantum simulation technique. So quantum simulation is not about simulating a quantum system on a classical computer. Rather, it is to simulate a quantum phenomena or a natural phenomena or a random phenomena which is very difficult or we are unable to simulate in a classical model. We aim that whether those natural phenomena can be simulated using a quantum computer or not. So that particular field is called simulation. And for security or quantum security, these are those algorithms basically where we in a very easy word, because we will be discussing about security, so in a very easy words it is a few of our classical security algorithms like encryption, decryption and all those algorithms are in threat. Why threat? Because the classical techniques, there are few quantum algorithms that can break that classical technique that we have. For example, the shorts one. Okay, so for which we now want to do two things. First is how we can secure our classical systems only so that we don't need to migrate to quantum. And definitely, so that means the same lock we cannot use to open the or same key we cannot use to open the lock. So that means it has to be new classical techniques that we want so that it can be quantum proof. And the second aspect of the quantum algorithms that are built on security is where we want that let us now let us now just have those notions of quantum mechanics, all the aspects like no cloning, entanglement, superposition, all those aspects, and let us devise something using the quantum particle, and that will be established on the quantum channel. Okay, so likewise there are, based on the requirements, there are different aspects of it. So quantum parallelism is what makes a quantum algorithm potentially faster than a classical ones. Now you should be knowing it. It has an entanglement capability. It allows superposition. So parallelism is equivalently, you can think it of as superposition. So superposition actually allows you to take like or to compute the operations in parallel simultaneously. So that is some sort of parallelism. And the dimension of quantum Hilbert space, the size of the state space is exponentially larger than the corresponding classical. So imagine the pizza story. We can keep on like dividing it, right? So though it's very theoretical, but again, theory, whenever theory is there, that means at some point of time there will be some realization. Okay. And that is the evolution of the quantum technologies that is taking place. So that is the thing, that dimension of the Hilbert space is not really under any control or under any barrier, because theoretically if we have very strong quantum particles, so we can exponentially increase the Hilbert space. Exponentially means if you have a 1 qubit system, or you can have a 2 qubit. So 1 qubit at 2 states, 2 qubit has 4 states, 3 qubits has 8 states, 4 has 16, 5 has 32. Likewise, say 16 qubits only has 65536 states. 20 is exactly 1 million, those many quantum states. So only if you have 20 qubits, you can have a 1 million state space, that much of a volume of Hilbert space you can actually have, right? 0000 till 0 within a kit plus 001 within kit. Likewise, 1 million times those many combinations or those many states will be there, or those many sub pizzas will be there. Okay, so all these three things give this much of power to a quantum algorithm. And this is the generic workflow. There will be a problem definition. Then you have to write the quantum algorithm, which is your logic. So the one who asked in the last class in the lecture 2, that means we actually fix it. If you remember, that was the last question, that we actually fix what we want. That is not exactly fully true, because you know, right now can see that you have seen the quantum circuit. I just have drawn some this kind of circuits to you. But the thing is how you can devise this circuit. So that has to be depending on some quantum algorithm. Now, do you really like if I ask you that please write an algorithm that can add two numbers? Will you really write the C code or the Python code only using 5 and 2, and that will be 7? So that means, will you hardwire it? Okay, the answer is no. That is not a definition of an algorithm. An algorithm means the logic will be same for no matter what or how you differ your input instances. That is the logic. So that means with respect to quantum, what do I mean by that is, so with respect to classical is, if it is at 5 2, you cannot call it an algorithm. It can be a problem instance. So the generic one is, or the algorithm is, say add AB, call by value I'm referring, add AB. So this means these are the actual parameters, and now whenever you feed during runtime, say 2 3, it will be 5. Then if you give say 4 and say 4, it will be 8. Likewise, your output will differ. First time it will be 5, second time it will be 8, right? Similarly, here as well in the quantum circuit, your quantum algorithm will be fixed. That say some kind of this, that first you have to do this, then you have to do this again. If it is dynamic, then you have to write a for, and those many times you have to do that. I'm not considering that, I'm just writing a simple one. So say C naught Q0 Q1. Say this is your what your logic is. Now when it will differ if you change the values of Q0 or Q1, or write some logic that will automatically say toggle a part of the qubit, and which will reflect in the quantum circuit. In that way the quantum circuit next will be framed, maybe a switch case, maybe a conditional loop. So that means depending on what flag values maybe you are just entering into the quantum algorithm, your quantum circuit structure will differ. Okay, so that means every time you are getting different quantum circuit as the output of a quantum algorithm. So the output of quantum algorithm is nothing but a quantum circuit. I hope it is clear till this part. Now you have got that in classical algorithm you got some value, where rather in quantum algorithm you got a quantum circuit. And what is a quantum circuit? It is nothing but a combination of quantum gates, right? Now once you have that, depending on the gate library or the underlying PMD, physical machine description, meaning whether it's a superconducting qubit or it is a some trapped ion, or say neutral atom, or some maybe linear or nonlinear photonics. So what is that underlying technological architecture? Depending on that, those quantum gates, say right now you can see one two unitary and Hadamard and a shift, say. So all of these gates will be decomposed using the help of a quantum compiler, right? And what a quantum compiler actually gives, some assembly code, just like the classical compiler, it gives those mnemonics, say add, move, sub, or say like sub, if, borrow. Likewise, all those like codes were there, mnemonics codes were there. Sorry, these were the output, like add, move, sub, leave, say carry, or say some kind of, these were the like symbols, right? Or and they have their specific opcodes, and operands of course will be having. And in I think QT-00 also you have some sort of like digital logic and those computer organization things, so you must be knowing it. So it's a part of the classical compiler. Similarly, if it is a quantum compiler, it will be some sort of quantum assembly. This is a classical assembly. And here we will be having the quantum assembly, where irrespective of what your like hardware or the underlying all these things are, it will actually decompose and write those simple codes, simple quantum codes, which will be definitely run by any of the quantum machine. Okay. And after that, you can do two things with respect to the typical workflow or the business case. First is, if you are allowed to pass it to a quantum processor, you will be passing it to a quantum processor, which is a real quantum hardware. Or you can pass it to a quantum simulator, which is a classical, say HPC or powerful hardware. Remember, quantum simulator is something that simulates the quantum nature on classical machine. But quantum simulation are those genre of algorithms that are built so that a quantum machine can simulate the behavior of the natural phenomenon. Both are very, very different. Okay. So this is a typical workflow, and of course, based on that. So right now, after this, you just have to do the measurement at this step. Do the measurement if required. Then also go for the post processing and all those stuffs. But definitely post processing and all, they are not typically quantum. So that's why in the generic quantum algorithm workflow, we have not written it. Right? Okay. Yes. So now, since you know this, I've kept a few ones so that I can discuss a part of the no cloning theorem and all. Then we will enter into the quantum algorithm derivation part. So I think by now you have, from the Bale state, quantum circuit and all, a very detailed understanding of superposition, entanglement, mathematically. And decoherence, mathematically, we cannot do right now. And no, another one is no cloning and measurement and teleportation, where I have covered all of this, but haven't shown you the mathematics yet. So today I will be covering these two already are covered. I will be covering only these two. I will left teleportation for the quantum communication part. And if possible, I will also do a bit of dense coding. Again, it if time permits. Because your syllabus for this is quantum computing. So that is why the very in detail quantum algorithm, if we discuss, it might actually not be very suitable for you, considering it's very fast QT-01, and you already had covered. We are covering the basics one like linear algebra, all those things. So definitely, I think a dedicated session will be there for quantum algorithm. So that's why I'm just picking up everything so that you have a brief idea of everything that you need to know in the subsequent chapters. So the no cloning theorem, which is very, very fundamental to quantum, says, so now you know one thing, that is a quantum state, if it is arbitrary, that was a claim that an arbitrary quantum state can't be cloned. Cloned means copied. So what do you mean? A little more deeper insights will be, say, I have prepared, listen very carefully, say, I have prepared a quantum state, right? Which is, say, any arbitrary quantum state. Say K0 have prepared. Can I prepare it again if I want? Answer is yes, because it's only simply K0, so it's 100% only zero. I can do that. Can someone else do that? Again, the answer is yes. So then, do we mean that this zero quantum state can be cloned? Or should we say that it is a no clone, violating the no cloning? The answer is no. Because of two things. First is K0 only is not any arbitrary quantum state. It's just the very basic pure quantum state, which is the initialization during the initialization time. So what we are referring here is that an arbitrary means it has to be somewhere in between the time evolution of these states. So during that Hamiltonian evolution or the time evolution of these states, if I want to do some kind of a cloning thing, then it will lose its property and it will ultimately collapse. Another one is, if I have, say now, second part is, say I have prepared a mixed quantum state during a particular time, which is say 70% 0 plus 30% 1. Now if I ask you, can I again create another psi with the same thing like 70% 0 and 30% psi, 30% 1? The answer is again yes. Why? Because I have prepared it. So of course I can do that kind of thing. So I'll prepare the kids and maybe there will be very little error, but at least if I know how I prepared the first time, 70% 0 and 30% 1, and if I again want to do that, I will be able to do that. So what do I mean by this? No cloning theorem is, if say I have prepared something, I am Alice. For example, I have prepared something like 70% 0, 30% 1. Bob knows about it, that Alice is going to send me 70% 0 and 30% 1. But say there is some third party, say Eve or eavesdropper, who has that arbitrary state, but he or she cannot really clone or exactly recreate these quantum state again because of these probabilistic amplitudes. So until and unless he measures it or she measures it from this superposed one, he cannot really predict that what was the like probability amplitude of ket 0 or what was the probabilistic amplitude of ket 1, so that according to the values of alpha and beta he will be able to recreate it and send it back to Bob. So this is not possible, meaning no intruder or no eavesdropper or no such person who does not have the preparation contextuality. Okay, so if there exists or there does not exist any, I hope you know this is a there exists symbol, and this is definitely the negation of that. So if there exists no, there does not exist any preparation contextuality. With that is someone who understands a context when it was prepared. With any intruder, he or she can never clone or copy or recreate the original quantum state, original arbitrary quantum state. As whenever, say, Eve receives it, she has to measure it. And on every measurement, or whenever Eve tries to measure, Q state will lost its quantumness and will be reset again. So that is the proposition for a no cloning theorem, right? Now say it means that if we have K0, which is a blank state, and there is an arbitrary quantum state psi, which I want to actually map using some unitary operator u, I want to clone. So this is the copy machine or cloning machine. So if it exists, if such an unitary operator u or that oracle, I know that you know oracle because yesterday professor discussed about this term oracle. So if there exists such an oracle, then that means that this copying machine or cloning machine should be able to actually clone this particular arbitrary state into your blank paper or blank state, right? Just like our Xerox machine, we give a blank paper as well as some say history paper, and when we call it a successful printout, when whatever content we have given in the history paper is actually copied or cloned in the blank paper. So if such a thing exists, that means in the output we are going to get what? The original history paper as well as the cloned paper. These has to be true. Okay. So if no cloning would have been supported, would have been supported, then that means this u get 0 psi, it will be able to map it to psi psi. Say this is equation number 1. So if such oracle exists, then that means just like the no cloning algorithm, say if there is another such say quantum state phi, that means it should also be true as per the equation 2. So therefore the inner product of psi and phi, I hope you know what we mean inner product, and what we get, always get a scalar product. Okay, so after this thing, so this is nothing but this basically. We can write it in this way. So this is bra psi and this is ket phi. Okay, so that means what was our initial one, like phi and psi, this thing. So can we write it in this way? Phi, then 0 0 we have introduced, then again a phi. Why we can do that? Because there is an identity. As 0 inner product 0 is nothing but this is 1 0 as a row vector, this is column vector 1 0. Just you multiply 1 into 1, and of course it can be done. It is a 1 row 2 column, and this is 2 row 1 column, so it's 1 cross 1 value. So it's 1 into 1 plus 0 into 0. So what is the value? 1. So 1 means we can definitely use this as an identity and we can put it over here. Now again, from this, so our state was psi 0 0 phi. So from this we can also write phi psi 0. Just I'm writing 0 with this thing, then unitary dagger u and 0 phi. And from again very basic properties of unitary operator, this is u dagger times unitary u will be identity matrix, right? from the basic definition of unitary matrix and all. If you do that, it will always be I. So now u dog dagger, this thing will be nothing but psi. Why? Because of the equation 1 of no cloning. And then this one will be, similarly, this will be, as per the second equation, phi. So which we can write in this way, that psi and phi whole square. So we started with this and we ended up with this thing. So when this is true, this is only true in two cases. If this has to be true, that means we can infer two things. First is the psi and phi both are same. That is, they are identical. Or we can assume that psi and phi, they are orthogonal. Why so? Now, or what if these two are the conclusions? So if they share some specific nature of association with each other, that is my phi and psi. So assume where we have started with. So that means our printing machine is not universal. There is certain correlation between phi and psi. That is why we can see that either psi will be equal to phi. If these two separately exist, then also psi and phi, that means they are the same state. So that means even if you exist or you can do that for one state psi, it cannot do the same cloning for another state phi. So that means there is no generic, no generic cloning machine exist. Or in other words, we can say that cloning, that cloning of arbitrary state is not possible. Therefore, quantum no cloning holds true. This is proved, right? Another very important aspect is measurement. Measurement aspect. So measurement is, say we define measurement operators being the positive. Just let me write a brief of the mathematical definition, then I will explain it with some example. Say we define some measurement operators. We talked about measurement outcome, why it is random. It is random. We talked specifically about it. If it is some superposed state. And so how to measure it? Right now we will look into how to measure a quantum state and like visualize it mathematically. Okay. Why we are looking into all these things? So that we can understand that what will happen with like effect of some quantum algorithm. So say we define measurement operators, say mm, as m equals to 1 2 followed by n, being the possible results of measurement. Means all these kind of outcome we can get. So if we say for a 3-qubit system, I can get either a 0 or a 1 2 3 4 5 6 like till 7. Okay. So out of all the 8, say, the probability of obtaining a particular outcome, say m, will be this thing, dagger that is measurement of the state m or outcome m, and psi. With an example we will look. This is very easy. It might look like this, but whenever there we will see it with an example, you can understand it better. But this is the probability of obtaining particular outcome m. And since all measurement outcomes, all measurement outcomes must satisfy the completeness equation. Meaning, with that same example, either I can go for having chana or reading book or going to watch a movie or doctor's home likewise. So all the measurement outcome, maybe I will be getting only one, but the measurement outcomes, and also maybe I have a little more biasness towards reading the book. So maybe all the remaining are 10, 10, 10%, or say 10, 20, 10%. So total is 40, but only reading a book has a probability of 60%. So it does not always mean that it will be 25, 25, 25, 25, but it has to be complete. Okay. So where this thing should hold true for all the measurement. And post measurement state will be whatever we have seen here, that is the this one. So root over of this thing, because this will be just to adjust it in order to solve the completeness equation. So it will be psi, the entire thing, root over of that, just like 1 by root 2 ket 0 plus 1 by root 2 ket 1. So it's ket 0 divided by root over of 2 plus ket 1 by root over of 2. The same thing. Okay. So this is that particular generic forms of measurement postulate. Now say I have two basis states, and they are ket 0 and ket 1, where measurement or outcome m0 is nothing but the outer product of 0, 0, which will be a matrix, and m1, which is for 1. And so psi, so this is arbitrary, such that say psi is equals to alpha ket 0 plus beta ket 1. Therefore, the probability of obtaining 0 or having a measurement outcome this is psi 0 and this 0 psi. So just look here. Okay. Why? Because PM, probability of measurement of M, or say PM, is equals to this thing, psi, then PM, then psi. And the same thing we have written, psi, then PM, then psi, where PM will be that M0, which is nothing but this thing. Okay. So from this, so now, and also remember one thing here, that is if psi is equals to the theory of complex conjugate, alpha ket 0 plus beta ket 1, this bra psi will be alpha star 0 star plus beta star then 1 star. Okay. So therefore P0 is nothing but, which was this, is nothing but alpha star, I'm just expanding this one, alpha star 0 star plus beta star 1 star, then this ket 0, and this 0, and then alpha ket 0 plus beta ket 1. So which is nothing but, if you look, so this, what is this one? Say alpha star 0 star 0 is nothing but alpha star. What I am doing, I'm just taking this one as well as this one, right? So this will be alpha star. Now ket 0 star, that is complex conjugate, is nothing but bra 0, and this is already ket 0, and this is the inner product of 0 0, which is 1. So this is exactly alpha star. And similarly, the second part, that is this thing with this, will be beta star in 1 star 0. So it's beta star. Now this will be bra 1, ket 1, and this is 0. Now again, if you do this, you look that it will be 0. The inner product of the different states. So 1 0 means 1 is this one, and this is 0 1. So it is 0 into 0. Sorry. Then this is ket 0. It will be 1 0. Sorry. So this will be 0 into 1 plus 1 into 0. That is 0. Okay. So likewise, so from this, lots of values will be cancelled out, and we will ultimately left with. So similar things will happen here as well. So ultimately we will left with alpha star into 1 into alpha into 1. That is alpha star alpha, which is mod alpha square. So this was your probability of obtaining a 0. Now therefore probability of obtaining 1 is same thing with a beta square. So now you understand that if we have this thing like say alpha or ket psi equal to alpha 0 plus beta 1, so what we call that the 0 and 1 are the basis states. This is the superposed state ket psi, and the probabilistic amplitude of 0 is basically alpha, and the probabilistic amplitude of 1 is beta, and the probabilities of obtaining 0 and 1 are alpha square and beta square respectively. So this is exactly what we have shown mathematically. Okay. Okay. I think it is clear to you little bit. Let me take if you have any queries in this part. Any queries till this part? Have you got it? Then we will look into the other things. Is it okay? Understood. So, okay. I will show my face. Don't worry. Okay. So I think technically same calculation happens everywhere. Then it is cloning. Yes. That is, we have to have devised some generic logic. If it is not generic, say I have for a history paper, I have a one printing machine. For math paper, I have another one. Then how can we call it a general printing machine? So there shouldn't be any concept of hard wiring. It should be very generic. So I hope it is clear. Okay, let me go back. Okay, let me just maybe created more slides here. I will remove it later. So now let us. So a lot of math part is over. For some more minutes, we will be discussing a brief of theory again. We'll go back to quantum algorithms. So a quick introduction. So whenever I know that yesterday you have some idea of the quantum algorithm and you have seen the Deutsch-Schwarzer, but the motivation is there are a few algorithms. Let me write it. At least there are this initially when the this kind of study or field to know the more about the quantum algorithms or the quantum logic, when that was kind of in pace. So what the researchers wanted is at least they opted for a little advantage in terms of mostly in terms of number of queries, and the problems chosen were also very specific and they were very basic as well. So out of those basic algorithms, so there are two different types of algorithms, not the paradigm. Two different type of algorithms. They were the very primitive quantum algorithms. So QA quantum algorithms are primarily of two types. The first one is the primitive one. Primitive, why primitive? Because of the maybe there. If you ask me that whether are they really NP hard problems and we have solved it, I will tell that answer is no. But it was just that exploration, or say you can say the footstep. When we entered into quantum algorithm, we really focused on at least how to devise it. What is an oracle? What is an ancilla qubits? How to measure something? So, like multiple what how to map between the input register and the target register. All those kind of technology or the technical things we wanted to understand. So, for which we aimed for a few primitive algorithms. And the very basic algorithm, first algorithm was Deutsch algorithm. Okay, named after the scientist who discovered it. Then he, along with his one friend called George Sa, I think that's the pronunciation. So they discovered another algorithm called DJ algorithm, which is kind of an extension of the Deutsch, right? There were a few other algorithms as well called the BJ or BV, Bernstein-Vazirani algorithm. Another one is Simon's algorithm. Okay, another one is the Simon's algorithm. So all these algorithms and these four are the only primitive algorithms that they initially discovered or created. And all these algorithms are with respect to some easy problems for which we might not need some quantum advantage, but it is just to show you or demonstrate you or to give you the essence of the quantum advantage and algorithm. Then comes the advanced form of quantum algorithms. So after that, till this point, there was no such limelight or spotlight on quantum. But after that, there were a few advanced quantum algorithms that were discovered. So what are they? They are your very well known Grover's algorithm. So I guess first one was Shor's, if I'm not wrong. 1992 or 1994, 1995. In between these like 3 to 4 years, there were these two milestone quantum algorithms developed. The first one was the Shor, which was for the prime factorization, and second one was Grover, which was for searching the unstructured and unsorted database. Okay, so that means unstructured means there is no such like a trick or say no such escape of using some indexing or kind of stuff. And why it is unsorted? You know that the numbers are not, or the digits, they are not in any order, neither ascending or not descending. And initially, when Shor was under like discovery, it was some n to the power of something to the power of n. Along with that, there are a lot of other such constant, and all other parameters are also there, but the basic function is something to the power n. And Shor came up with a n time solution, which was an exponential, like kind of advantage or exponentially better solution. Okay, and Peter Shor was a professor of, he's still a professor, I guess, at MIT. I guess at MIT, yes. So mathematics department. So he discovered this idea, and just within a few years, his another student called Love Grover, he came up with another milestone algorithm. So till this part, there was no such supremacy. Shor first time bring the supremacy. Until that point, everyone was also at rest. But when they have seen that our RSA or all our security system, whatever we use, or even whatever our existing blockchain technology and all these things use, all are based on some RSA and these kind of classical algorithms. They can be broken by Shor. After that, there was so much of traction around quantum that we have to do something. Okay, so that is some sort of milestone achieved in quantum field. Second one was Grover, which is, as I mentioned, so it was for the unsorted, unstructured database search algorithm. So we call it finding needle in a haystack. So if it is a very, 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 very large database, say for example, and right now, in the emergence of big data and all these things, ChatGPT and all, so data size is going to increase exponentially. It is increasing every day. Okay, and in Moore's law also, in the first class we have seen that the size, the way the data size is getting increasing, that is not the way our chip size is actually maybe increasing. So that is what is a big challenge. And in that much of a large database, our classical, what is the best known classical search algorithm, considering we do not give any provision to use any auxiliary memory? What is the best known classical algorithm? We all know that it is the log n, considering we have a sorted. But if it is no such sorting is given, then it is order of n. So log n was binary search, order of n is your linear search. And there is no such improvement in order to, so with which you can make it even better or less than n in terms of complexity. You cannot do that. So Grover came up with another logic. He through a lot of such techniques, and the algorithms are really very, very, very complex. He discovered some technique with which the n complexity has now been reduced to root n. So maybe for that means, in the worst case, if it is some array of size n, you can find some data in order of n time, or order of n, or n minus 1 number of queries. So n number 1 is basically, so if it is n minus 1, so basically it is order of n only. Okay. So, but Grover can solve it in root n time. Okay. So this was the algorithm evolution in quantum space. And there are few more algorithms as well, like HHL algorithm, like the Harrow-Haslym-Lloyd, which is used in quantum machine learning. There are QAA, a lot of such algorithms are there, right? But nothing is really that great as Shor and Grover. Otherwise, you would have heard more about these algorithms as well. So QAA is based on some quantum aided optimization, which relies on approximately better solution. So it is not exact better. Similarly, this HHL, it is again theoretically quantum advantage. It can quantum supremacy or exponential speed up it can give, but there are a lot of other constraints associated with HHL. But so far, it is the only most primitive quantum machine learning algorithm, the Lloyd's algorithm, HHL. But as I mentioned, nothing is like Shor and Grover. So now comes the quantum algorithm paradigms. So what they have done is they introduced their own paradigms, okay, in order to solve it. So the paradigm discovered by Peter Shor, and used in Shor's algorithm is known as quantum Fourier transform, QFT. So now you might, as a researcher, think of say solving some problem where we will be using some subroutine or subpart, or try to modulate or manipulate or say anything, whatever you can imagine in that way, or enhance or extend this QFT technique. Okay. And there is another one which is which also was derived by Shor, called quantum phase estimation, QPE, but it is also some way say reducible, not exactly same but reducible to the concept of QFT. It's part of a inverse QFT and with a few modifications. So initially, that discrete Fourier transformation was there where we actually worked on the frequency and time signals and all. So those who have some knowledge about signal processing and all, so you might be having that understanding, Laplace transform and all these kind of Fourier transformation, discrete Fourier transform, all these things. So Shor first came up with his version of Fourier transform, and he named it as a quantum Fourier transform. Clear? Second one is what Grover has come up. So Grover has come up with another paradigm known as amplitude amplification, quantum amplitude amplification. So I got one question in second class, that can we exactly, when we were doing the quantum circuits, hand drawing the circuits and was doing the calculation, one asked me that can we exactly measure 010? Is it possible? If you can recall, one of the participants asked that question. At that time, I mentioned that no, we cannot do that. Our measurement always has to be very random. And I told you that if you have to do that, you have to do some tricks. You have to really modulate your quantum circuit through some changes so that it remains in superposition, because once you measure it, it is like quantum is gone. So it will be in superposition, but one of particular amplitude of particular quantum state, or a very selected number of quantum states, their amplitudes can be amplified even if, or even when, all the quantum states will remain in superposition. So how to bring from during the evolution, you will not do any kind of measurement, you cannot tamper the system or qubit or the photons, you can do nothing. So during the evolution, through some technique or a series of techniques, we actually can enhance the amplitudes. And what is the result of that? Whenever you are increasing the amplitude significantly with respect to the resultant states, you can tell, say 0.00001, all of them have very, very low probability, say 0.001925 or 0.0291. Likewise, only say your state 110, which is 6, has some probability of say 85.96%, 92.5 some percent. So of course, now you know that your unbiased quantum state or your uniform superposition, you actually have introduced some biasness with respect to a few desired state, and also have introduced a non-uniformity in the superposed one state form. Okay, that is the amplitude amplification. Then these are the algorithms built on the quantum simulation. The quantum simulation one, which I was talking about. Till now, there is no such very significant improvement. So it is under, say, under improvement. Algorithmically under improvement. Okay. So all of them are under improvement, but algorithmically, this is also in under, like high level of R&D is required here, because it is very, very challenging, a very natural phenomena. If you have to like simulate it in a quantum machine, because quantum is also random, so both random mapping to random things, and we have to, for that we have to undo the way we think classically, and that is also not yet done. And natural phenomena, they are very like fragile, they fluctuate, they are, maybe that much of mathematics also is not known, that how they are devised, so how we can map it, that's why it's very challenging. But QFT and QAA, the first two, they are algorithmically 100% ready. But here what we challenge we face is the hardware level challenges, not the software or the logical level. Fourth one is the adiabatic algorithm. So adiabatic process, that's something very slowed down. Whenever you slow down something in physics, we actually heard of the term adiabatic and adiabatic properties of some material or some temperature curve. If you look into that, so it is initially everything is very much in an excited state. Okay, but as and when we move on or we let it actually maybe precipitate in terms of the performance or in terms of some settling down or that all the temperature and all, or say for example the ground state and the excited states of atom, so everything is very stabilized or settled down in the ground state. So we actually keep on dissipating energy, and we keep on like coming back to the core or the nucleus. So likewise, with respect to time, these adiabatic properties of quantum materials or quantum things can also help us to get into the our desired state. Now you might be asking question that, okay, like that is in terms of temperature, in terms of physics, but in computing or in algorithm, what do we mean by that? Meaning, this actually is used by D-Wave. This is a Canadian quantum computing company. And you know that in Canada, the temperature itself is so soothing because we need very, very low temperature, very cool temperature is required. So that is why actually they are working. And this is even working, I think, before IBM or when they developed their annealing model, which is based on these adiabatic properties of materials. That was something that they are working beyond, like when IBM or all the Qiskit things work. A lot before that, this company is working and they developed their quantum computer. And in right now also, last time I have watched it, maybe 5,000 or maybe right now 7,000 or 5,000 or 7,000. These many number of qubits are there, what these companies have. But definitely, IBM has say 127 qubit computer. Now you might be asking question, then how can IBM, why there is so much of hype around IBM or say Google search and all these things? The answer is because the computing model that IBM uses and D-Wave uses is very, very different. Okay, so despite the fact that D-Wave has a 5,000 qubit say quantum computer, it is very noisy, as well as a lot of those qubits every time you cannot use. So there are a lot of like hardware things there, and what kind of problems you can feed into the D-Wave machine, which works on this annealing model, is also very different, because annealing model is based on the physical properties, right? So not all problems you can feed into the annealing model, but there are a particular genre of quantum problems that you can feed, which is optimization. And since more number of instances we can feed or we need in optimization, that is why you will look that the industries that are working on quantum optimization specifically, they actually prefer your D-Wave. So there is no such direct comparison. We cannot compare the performance or efficiency of the D-Wave as well as the other quantum giants like IBM, Microsoft, Google, all these companies, because their technology is like both their computing models are different. Their technology, both of them follow superconducting qubit, that Josephson junction, and the physics is same, but the way they devised their model of computation is different. D-Wave follow adiabatic model of computation. Okay, so for optimization problems, what they do is they actually the best solution, the best optimal solution, maybe they actually encode it in as the ground state, and then they prepare their state as per their logic, and they prepare it in such a way that every time whether the minimum cost wala solution or the minimum time wala solution will be encoded or will be ultimately obtained as an optimal solution as the ground state Hamiltonian. Okay, so there are a lot of maths of that. I'm not getting into the adiabatic model right now, but this is the nature of the adiabatic. So the optimal solution will, every time we will converge to the optimal solution, because we will encode the optimal solution into the ground state. And every time, no matter where we're starting with no matter where excited state we currently reside into, we will go back to the ground state. And how we will do that? Adiabatically. Hope it is clear now. And the last one is based on the quantum walk. Quantum walk is the quantum analog of classical walk or the classical random walk. I'll do a little discussion for this. Okay, I will discuss quantum walk. There are some examples that I have, like diagrammatic representation, with which it will be easier for me to make you understand. Okay, I think we can take a like 2 minutes break, and we can start at 4:17. So we've covered this part. So let us now take a little break. So I'm stopping sharing, and we will again start at say 4:17. Just a little tea break, water break, whatever you call it. There are a few questions. Let us take the break, then we will answer it. We'll start with that. So we'll again meet at 4:17 or 4:18. Be on time. Okay. Yes. I think we can start now. One asked some question that adiabatic algorithms need to run really slowly in low ground state. No, no, we are not physically slowing down the algorithm. We are not doing anything with the algorithm. Algorithm we have to like prepare in a way we just encode our solution space. The entire see in quantum what happens is what output you will be getting has to be encoded somewhere in your system only. Only then you can have that as a solution, right? So it has to always be one of such solutions. So problem encoding in quantum is not exactly the way the classical ones work. You have to encode it. I will explain one algorithm. Try to do the mathematics. I will explain it that how we can actually encode it. And also remember for the adiabatic one, the computing model is completely different. Here it is the universal model of computation, the quantum gates, quantum circuits, the way we see here. It is not exactly same as the adiabatic model of computation. So in IBM Qiskit and all, it is the universal model of computation. That is why we mostly use it. But for optimization problems only, we at times prefer D-Wave. And though honestly, I will not say something very great you can do with that because there is no comparison. So you have to wait ultimately for a better solution. Okay, I think you have got it. Like we are not doing anything with the slowing down the algorithm or all, not at all. Okay, I think let us again go back. Why? Like for the last 10 minutes, I was using this same slide. Okay, I have not changed it. So these are a basic essence of it. So you can see this is a like QFT circuit, quantum Fourier transform circuit, which is a part of subroutine used in short. So I cannot explain it to you, neither you will understand it. So I will skip it right now. But as I mentioned, quantum Fourier transform it's a quantum analog of the classical DFT, discrete Fourier transform. And QFT means by using a simple decomposition of like the discrete Fourier transform on amplitudes can be implemented as a quantum circuit consisting of Hadamard and controlled phase shift gate. Forget about it. Whenever you will look into shore, you will of course be introduced with QFT. Whoever has done that or will do that. So just remember one thing. This is all these n qubits. So this is your Hadamard gate. So right now you should be able to only identify it. This is the unitary rotation, which is controlled. So far, if you understand this, I think that is only good. So this is the control, and this is your target. Where in target itself, you are just rotating it. Okay, this is the thing, and nothing else can be explained right now without a deep dive. Quantum amplitude amplification. This is the geometric one. If I explain Grover, I will ask you, all of you, that what algorithm I should be like showing tomorrow. I think tomorrow is the last class for us for computing. Remaining classes are for like communication. So only one algorithm we can choose, either Grover or Shor. So whatever you say, accordingly, I will talk. And depending on how many more classes I have. If it is 4 hours, then only we can, I think, speak. Okay, so this is the initial one. See here, this is what I was referring. So this is uniform superposition. This is the selected state. This is our target state, which you want to amplify. And through some QAA, actually it's Grover operator, Grover rotation operator. Okay, through some unitary operations. This is not in a single step. Okay, we can actually make these particular amplitude be increased. Something like that happens. Okay. And the number of complexity is order of root n. Simulation algorithms, just have a look into that. Adiabatic algorithms. And okay, one more thing I want to mention, the concept of tunneling. Tunneling is, if you know, concept of simulated annealing. So in simulated annealing, in computer science, you must be having that concept of simulated annealing. So there is one problem with simulated annealing, and this is one of the techniques used in optimization and all, the simulated annealing. And what is the problem there is we often are stuck with local optima. We cannot see because whenever every time we assume or we actually are fooled by thinking that maybe we this is a convergence point, but you do not know maybe just after another iteration or say two iterations there is a better solution. But simulated annealing technique works in a way where you do not have the provision to go beyond one local convergence is obtained. So this problem basically will not happen in quantum because of the quantum version of simulated annealing, which is called a quantum tunneling. So in very easy word, for problem statements of problem instances like this, just say this curve. Okay. So in classical, what happens? So which is a optimal, global optimal? This one, and this is your solution. But in simulated annealing, if you are here, you will assume that okay, so in this particular curve, this is the best one. So I have got my solution. But you do not know that here you have even better solution. But in quantum, because of a tunneling effect, we assume that whenever we are here, say this is one, we are also here. That is, we can tunnel through between the system. And why? Because of the same de Broglie hypothesis of light. That is, it has not only the particle property, it has the wave property. And wave means you cannot really restrict it. So with a certain frequency, it can move, right? So wave is a very continuous thing, kind of. So maybe the probability that with which I will be here one is 80%, but you really cannot null out that the probability that it will be in place two is also 20%. Because of the wave nature of quantum, we call it like as if it has tunneled through multiple states. Okay. Now whenever also it is here, now whenever you can be from here to here, that means you will fall down, say A, B, C. So you will fall down at B because you have to settle down. It's an adiabatic algorithm ultimately. So you will be again settling down and you will think that okay, this is the better. But whenever you think that this is the better one, you also with certain probability will be here. Whenever you are here, you will again settle down. If there is no such better solution ever existing, so you will ultimately say that whatever is my ground state, and you see this is the ground state, that means because energy is increasing. So these are your excited states, excited energy levels, and this is your ground state. So even if say there are something like that, so it will not tunnel through, or whenever if even if it is tunnel through, ultimately when you measure it at the end of time, you just measure the ground state because you have assumed that in ground state only my solution can be. And this phenomena of quantum, this is not very hard, like a very kind of very primitive phenomena like superposition entanglement, but this is also one of the very important features which has a great implication in optimization. Okay. Yes. Now the fifth one, that was the quantum walk. So I mentioned that quantum walk is nothing but the quantum analog of classical random walk. Don't ever call a quantum random walk because quantum itself is always random. So quantum random walk is like a kind of, okay, I'll not get into that example. So a lot of people in Bengali actually, where they call like where they call something that is government service chakri kore. So since I'm a Bengali, so this is a wrong statement because service means itself is mean service. So it's just like in English it might like sound like government service. So don't ever call that quantum random walk because quantum itself is always random. Okay, jokes apart. So this is a random walk, and this is very time dependent random walk. So it either it can be discrete time random walk or it can be continuous time random. So continuous time random walk and discrete time basically they are very they differ by the time interval between two consecutive steps. In more technical words, so discrete means say after every 1 minute I will make a step. So it's very discrete. You can visualize it. Then what about continuous? Continuous means here also you are actually taking a step after a particular time interval, but that time interval itself is so minimum that it appears as a continuous time work. That is the only difference. That it should be having some smooth transition. It should feel like, it should look like very smooth transition. Okay. And similarly, there is a quantum work which is the discrete time. Okay. Sorry for that. So this is a discrete time quantum work and continuous time quantum work. See here. Okay. Okay. So physical intuition between a behind a classical random walk. So just say from like a walker is actually walking a person. So he's at point one. So the probability at time instance and these are the time. So at time zero, the probability that he will be at vertex one is one. Absolutely, that is it is 100% probability because there are no alternatives. So from one I can either be two or three. So it's a half and half probability, 50-50%. Now again at point 4, from 2 and 3 both I can converge to 4. So it's at 4 I can be at time instance 2 with 100% probability. And similarly it will be at 5, 6, half and half. So likewise the probability of vertices will be changing. Okay. Now in the discrete time quantum work, we call it like a drunkard's work. So it uses superposition as well as some conditional operator very in a very controlled way. It's a drunkard work. So a person after getting drunk, the way it works, as if the quantum walk appears like that. So that is at each discrete time interval, quantum walker is affected by an unitary coin operator that is left right. That is how a drunkard works, right? He doesn't have any specific direction. Sometimes left, then right, then from right he can either go to again and left or right, or from left also he can either go to a left and right. So likewise, the work is very kind of an haphazard one, right? So it can be like say this, then again this and this, and something like that can happen. So this is I'm not drawing it exactly. So this is not exactly like that, but yes, just like a drunkard. So uh, yes, let me remove it. Yes, okay. That's why I don't use it. Okay. So, just a minute. Let me again come back. Yes. So this is like this thing. So we use two different operators. First one is the Hadamard one. We call it a coin operator, tossing a coin. And second one is the shift operation. We call it an ace operator. So the thing is, Hadamard operation. You know what Hadamard does? Hadamard, if we have given zero, it will make it get 0 plus get 1. I'm not writing the 1 by root 2 for simplicity. And if it is Hadamard 1, it will make it K0 minus K2. Again, I'm not writing 1 by root 2. So that means this is your current position. Same. So there are two operands for this coin operator. So the second one, it will make it either a 0 or a 1. So this 0 is now become K0 plus K1. Similarly, this 1 has now become K0 minus K1. This is the effect of coin operator. And the effect of shift operation is, if you are at state X and if you get a 0 on right, then you will just take a left step. Okay? You will go back one step left. And if it is a 1 on right, you will just go one step right. That is, either it can be a left or it can be a right. Okay. Now, let us look into this example. So this is shift Hadamard 3 times. Shift Hadamard, shift Hadamard, and shift Hadamard. And then 0, 0. So now each one, first I will do this, then I will do this, then exactly this thing, then this one, then this, and then this one. Likewise, we will go from left to right, from right to left. So this 0 under Hadamard, it will be 1 by root 2, get 0, 0 plus 0, 1. This 0 will now become 0 and 1. Now, what will apply? And 1 by root 2 is, of course, there. So now you will apply this shift operation. What does shift say? If you have a 0 on right, you will just decrease it by 1. That is, you will go one step left. So that means now your 0 will become minus 1. And if it is 1, it will increase by 1. So it is 0 plus 1, it is 0 minus 1. Okay. Till this part it is clear. Okay, let me now just take this one. Say, okay, now I have to do a Hadamard. Okay, let me just write here itself. So I'm just writing it, you just see it. So now this 0 will become 0 and 1 first. So it will be minus 1, 0 plus minus 1, 1. And then, and this is the effect of Hadamard. It will be plus, for this one, it will be 0, then minus 1. Nothing else. So first one will be as it is. So it will be this one, then K0 minus K1. Okay, this thing. Now you will be applying a shift gate again in the next step. So what will happen if it is a 0? It will be again decreased by one step. So it will be minus 2, 0. If it is 1, it will be increased. So it's minus 1 plus 1, that is 0, 1. If it is 0, again it will be minus 1, that is 0, 0. And if it is 1, it will be increased by 1. So that is, it will be 2, 1. And likewise, you can go. And this work is called Rutherford's work or discrete quantum work. And this is what was shown here. Left, right, likewise it will toggle like this. Something like that. Okay, these are few things. I kept it. Okay. Okay. Now the diagrammatic representation of the same thing, the discrete work, DTQW, is shown here. You see that? Okay. And this work, the example of this one, what the real problem is triangle finding problem, where ultimately in this kind of a complex circuit, you have to find that kind of some cycle of size 3 you have to find. So it's a decision making problem to decide whether a graph contains a cycle of size 3 or not. Okay, this is one of the application of DTQW. So there are different approaches, and it also actually incorporates a part of Grover. That is why I talked that the first two approaches are the most unique one, the QFT and the QAA one. And the second type of quantum work, which is CTQW, remember it's continuous time. That means there has to be some hopping rate, and we want to reduce it as much maximum as possible. So it affects by a factor gamma, and these are two different adjacent vertices. Okay, so how we transition, that is the case here over here. Again, this is a lot of such things. We actually worked on that, and there is a very important problem called random welding, where we actually there is an entrance and there is an exit, and we basically the target is that you have to find the best next word. So right now you can might think that something in the chat GPT, or like word prediction, something that matches maximum, or what should be the best welding for that particular word. So this is very much in use for search engine optimization and all. So where two search trees. So this is one search tree. This is one, and this is another search tree. So this is one keyword, and this is another keyword. Now, and these part are the random welding. So how to establish that? What should be the best welding thing? So based on that, I worked on this one during my BTech. So and you can see, I'll not explain it. It will be difficult. So you can see that there are a lot of like some controlled and multi-controlled profoligates, if you can understand. Okay, and that is how actually, and but the challenge that we solved here, actually we tried to make the dynamic welding generic. The just the quantum logic or quantum algorithm we worked so that this can be made generic, the dynamic welding, and we can devise a generic quantum circuit for the dynamic welding. Dynamic welding means what will be the combination that will be random to us, but we have to devise based on the entrance and exit or these pairs, and that how generic way we can devise the logic in such that the control target relationships can be established. So that is called a multi-control topology. We worked on that. So similarly, our system was able to tell you that okay, these are the gates that we produced of a like 4 qubit. You can see like input and output, just like control target. So from these like series of decomposed quantum gates or the MCTs of size 4, we can actually say that what are the adjacency of the matrices, or how the welding can be established in a quantum circuit. Then comes a quantum machine learning, or its importance. This is one application of QML, which is a quantum recommendation system. And in Netflix also, you have seen the most best example is Netflix, where there are n users and n films, and the goal is to recommend a film to user that they have not watched. So for these kind of problems, these are a part of that. And you can see it's a polynomial. Poly means a function of. It's an f of something. Okay. And then a poly of log of mn. So it's a function of, if it is an mn, if it is a function of log of mn. Right? Just like say fx is equals to say x minus x squared plus x to the power 5 by 4. So f of log x is nothing but log x minus log x squared plus log x or 5 by 4. So you can see there is a exponential drop. And the algorithm that does this is, and the classical, okay, just a minute, and the classical perceptron model as well. All of you, I think, know that what this kind of structure means. These are the weights, these are the inputs. Ultimately, this is the decision that you take, and these are the activation function and all, right? So, for these basic models and all the, I just mentioned PCA, principal component analysis, also in support vector machines. The classical ones uses this, and the quantum one uses this. So, likewise, this is a poly DN, this is a log of DN. Okay, so there is a huge difference that way. So exponential speed up is also possible in multiple such machine learning applications. Okay, and this is for the supervised one. Again, for unsupervised also, quantum algorithm can offer better advantage than the classical. All the three cases mentioned above use HHL or Haro-Hasidim Lloyd, three scientists who discovered this algorithm as a subroutine for a quantum linear system. And there are all these things that is in use. That is why HHL itself, realizing HHL is very difficult. So it uses everything: QFT, then simulation, then phase estimation or QPE, then phase kickback, then QAA, and then followed by some uncomputation trick. Okay. So this is one algorithm which maybe uses the maximum number of paradigms. Now, quantum itself is so right now tricky. So this is like all good situation in one place. But already one such paradigm, implementing one such paradigm itself right now is so hardware kind of dependent. So that's why you will see a lesser words for each HL, nothing else. Okay. So this is the end of slide, but I will be explaining. So where I can do that, I think there are a few things, that few pages I left at the very beginning. Let me go back. Here are four one. Yes. So this was the end of that no cloning and measurement postulate. So let us now start one quantum algorithm. Okay, that from the primitive set. So what we, because you already have seen the Deutsch-Jotzer and Deutsch algorithm, Simons also has said that he talked about the problem statement to the power inquiry to inquiry, that kind of mapping Sarah has already mentioned. So I will be talking about the Bernstein-Waziran. Okay, so this is also another trivial extension of the Deutsch Jotzer itself. So it's called the Bernstein-Wazirani. Okay, so it will be a little mathematical. You can understand that. So please just focus. So it's a trivial extension. So DJ has a trivial extension. This is Deutsch-Jotzer has a trivial extension in this BV, Bernstein-Wazirani. So the problem statement is that given an n-qubit input string, what does that string say? Ktex is equals to xn minus 1, xn minus 2, dot 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 x2, x1, x0. From LSB to USB, it will, this is how it will look like. And now we have to find an unknown string A, say, such that A also is like a n minus 1, a n minus 2, dot 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 a1, a0. Just notice once, because we just have talked about that a solution encoding in quantum algorithm is the most challenging task. So that means A and the input register X has to look a little similar, rather exactly similar in terms of bits and all. So after that, just like the maybe apple and mango, we cannot compare. If you have to compare some apple and mango, then you have to either convert the apple to mango or encode or mask your apple so that it looks like a mango, and vice versa. So here also, that is where, that is how in quantum amplitude amplification only one quantum state under that superposed state you can see as output, or your quantum oracle that can also work. So if the two, what you want to find and where you want to find it, like the entire solution space, if they differ, if that is not at par, or if they do not sync, then your encoding is not possible, and without encoding your algorithm will not work. Okay, so you have to find an output string or unknown string a, where these unknown strings information will be given to oracle. Okay, such that your f of x is equals to a dot x. What is a dot x? It is the bitwise product. Meaning a dot x is nothing but a n minus 1 x n minus 1 plus a n minus 2 x n minus 2 plus a n minus 3 x n minus 3, likewise a0 x0. This is the case, and you have to find the unknown string such that fx is equals to a dot x. So in very easy words, if you remember in Deutsch, very basic Deutsch algorithm, we had used only one for one input string or for one value. We have checked that whether fx is 0 or 1. So it is whether a balanced function or a constant function. Then we have seen the extension in Deutsch also, where it is like for multiple one. That is, our entire space can be divided into two parts. And how many of them will be a 0, and how many of a few of them will be 1. If that count is exactly same for all values, then we will call it a constant function. Otherwise, we will call it a balanced function. Now, for this, in classical, we need a lot many number of queries, but we have seen for both Deutsch as well as Deutsch also. That is for 1 qubit and in qubit, the number of queries is exactly 1. So that is some good kind of an advantage that we can see there. Now here, it is not about whether fx is balanced or constant. Here it is, you have to find a secret string such that there is a bitwise product relationship between that particular string and all the other like input combinations possible. Okay. And bitwise product, one thing I missed, it is mod 2. That is a XOR, basically XOR. Okay. Now, the logic is, let me just write it separately here. So it also looks very similar. There will be a oracle here as well. So one unitary function. This is also called oracle. So there will be all these kind of zeros initialized. You have to do the initialization. You have to put header mart. So it's header marted input. Only one value, the last one, which is a target register. You have to keep it 1. Also have to pass it through some header mart. And the output that you are getting, you have to again put the header mart and have to check. Right? Okay. Let me write it. So we have fx is equals to s dot x, and we have to find s, a dot x. So whatever you write, we have to find s. So it is, from this we can understand that it is QT-00 product tensor product n, that is 10 n number of times product 1, which is the target qubit. And this entire thing is your initialization or initialization, well, registered initialization, whatever you say, Q registered initialization. Now you are putting Hadamard on all of them. So on this, on writing Hadamard, it will be 1 by root over of 2 to the power n. Don't get confused because I'm just writing the generic ones. You can break it, you can take 2 zeros and check. It will be 1 by, ultimately, what it will be, 2 to the power 2, that is a half. Okay, so I'm just writing it in this way. X equals to 0 to 2 to the power n minus 1, then x, and this one will be 1 over root 2 ket0 minus ket1. So if I merge all of them together, it will be something like 1 by root over of 2 to the power n plus 1 for obvious reasons into x to the equals to 0 to 2 to the power n minus 1, it x product 0 minus 1. So now we are applying oracle, which means oracle will do what? Oracle will perform the f, right? So which is your x into y. This is a generic form. Oracle will make it the UF, it will make it x and y's or fx. By now you should be understanding that y, and this is from the very basic definition of oracle, we can write that. And if your fx is, let me write here, now if fx is s into x, then ket0 minus ket1, can write it in this way, minus 1 to the power, say, fx, then ket0 minus ket1. Of course we can write it, since your y is equals to y's or f of x, and of course we are ignoring, let me write, ignoring 1 by root 2. Let me cover the full part. And also, since this is unchanged, we can ignore. We can ignore it. Therefore, the important effect that we can see is ket x will become minus 1 to the power sx into ket x. The ket0 minus ket1, all these parts actually has no such much of the changes because fx is s into x only itself. So that will not have some more effect. So quantum, therefore, quantum state after oracle will be what? 1 by root over of 2 to the power n into x equals to 0 to 2 to the power n minus 1. Whatever I had initially, this entire thing, right? After oracle, 0 and 0 minus 1 we will not introduce, but we will be introducing this thing into x. Now after oracle, what we are doing? We are again applying Hadamard on all the qubits. So that means if I have to apply Hadamard on all qubits, that is 8 or all n qubits, we are applying an Hadamard x. So that after that it will be 1 by root over of 2 to the power n. Then it will be, say, y equal to 0 to 2 to the power n minus 1 minus 1 to the power x into y times 1. Okay, so we'll be applying this thing. So now we can substitute this thing into x times x, and now expanding this, on expanding it will be 1 by 2 to the power n. Then few steps are nothing but algebraic simplifications. This is n, this is also n. Okay, and then minus 1 to the power s into x into minus 1 to the power x into y times get y equal to 0, and this will become sigma x minus 1 to the power s into x plus, of course this will be added up, x into y, right? And this only, if you look into it constructively, interferes when your y is equals to s. It's whatever y you are obtained, and this is the same s that you want to obtain, leading to your s. Therefore, we can say the final quantum state is get s. And now if we apply a measure gate on s, we will obtain the secret string. We will be obtaining the secret string with 100% probability. And that is what we want to get here. On measurement, we will be getting this one. This is the mathematics of Bernstein-Vazirani, but I can definitely understand that it can be little problematic for all of you to find it very easy. And the reason, trust me, is only because we are taking only the generic terms. Now, from wherever we have started with Bernstein Vazirani, what I would want is, for just before tomorrow, you can try one thing at home. That is, you can try to take a very small string with specific values. Okay, take a 3-qubit system for example, then take specific values of a secret string, maybe say 100 you want to find. Then whatever we have done, try to follow the same steps, and then check that whether you are obtaining that 100 at the output or not. Okay, okay, that's something you can check. And for that, what I have planned is, tomorrow we will be doing primarily two things. First is, we will start with the same example. So you do it, you can do it with any secret string. You can try if you want to. Maybe I will be also taking 100 or 101 or 011, any such value, and I will show you the exact example of Bernstein Vazirani. That it is not really this complex, because we are using a lot of sigmas and all Hadamard, the tensor products. It is looking a little complicated. Today, I've thought of that I would cover that, but unfortunately, there is not much time, and it would need at least 20-25 minutes. So tomorrow, I will start with this example. I'll be sharing all of you all the slides, skipping, removing the white slides, and also one of the difficult algorithm, maybe Grover or short, we will be doing tomorrow. That is some plan that I have. Okay. I think I'm done. If you have any question on mind, you can ask.
Thank you so much, ma'am. Wonderful session. Visualizations were also very nice. I hope participants could follow them very smoothly. So in case of any questions, participants can write in the chat box right now. Otherwise, ma'am is going to conduct session tomorrow also, so you can ask questions tomorrow. So couple of questions are coming up, ma'am. So if you can answer them.
Handwritten, yes. First of all, I'll be sharing the handwritten. I'm just keeping all the annotations here itself. Likewise, only I'm sharing. Okay, and okay, what I got only one question. What does -1 represent in random walk? No, -1 represents in random walk is that it is the left. So these are all the representation, right? This is not the direct like quantum circuit or any such quantum gate thing here. So this is how we are just encoding the logic. So it is just the left and right. Likewise. Okay. It is not like -2 0, how exactly it will be visualized. For that, it is a separate logic altogether. -1 is just representing that it is the left. It is the left shift. Just the number line 1. It's not only kit -1, it is like -1 comma something. So it is just the representation of the quantum state that it is in this particular point. Now we have to encode it. That encoding is also like a separate one. You remember the drunkard's work? Whenever we were doing it, we were actually using a number line just to show that how it works. So similarly, because there is no such coin operator, so it's a like complicated one. We have to, for implementation, there are further considerations. Yes. Anything else?
Okay, thank you so much, ma'am. So we'll continue tomorrow, and all the participants are requested to join tomorrow at 3 p.m.
Yeah, we'll continue the same lecture by Nivedita ma'am, and she will continue for few more lectures. Then we will go back to quantum communication and quantum sensing materials will complete. So ma'am will take another 3-4 lectures. So hopefully all the doubts have been cleared. And if there are any issues with reference to Canvas or with reference to this thing, I think some of you have still not paid the registration fee. Please, only for the certificate you need to pay. Course is free anyway, so that is there if you want the certificate. So that's why please do that. And if there's anything missing, you can write. Yeah, Prasad sir, thank you. Vizag was very good. I could not see the beach. That was the only thing. I just took the lecture and had to fly back immediately so that I could be on time here for today's lectures. So it was good, and we spoke on quantum hardware. Maybe I will share the slides here so that you can enjoy. So actually, a lot of some of the content that on the first day, I think Richa Goel madam had covered. So I could share some contents there. So it was nice, right? Thank you so much.
Sir, if you want, you can start with exploring Vimley Beach. That is very good.
Beamly, yes. I have not gone to Beamly.
Yes,
Yes,
it is even
not
better
that.
than the RK Beach, to me at least. It's very good.
Correct. We should
And
go
some
there.
Thutlakonda kind of some beaches also there during the
Rishikonda,
Holi.
Rishikonda is
No,
there
no,
one.
not Rushikonda is even a little crowded, but there is another beach called Thotlakonda, if I'm not
Okay.
wrong,
Right,
the
right, right.
pronunciation. Yes, it's also very good.
Good. Yes. So yeah, people are appreciating your experience. Today's class is good. Yeah, actually, once you start listening more and more, you will get that confidence. That's what I'm telling. Please, the only way to build confidence in quantum is to listen more on quantum. Right? Please keep listening. Videos. Please listen. Read the slides again, and then you will definitely get. Yeah, okay. Raghavendra sent a WhatsApp message. We'll just check your this thing and then we'll add. Anil sir, yeah, please.
Sir, good evening.
Yeah.
Sir,
yes.
actually, we missed you. Yesterday, you were at Andhra University,
Yes, sir.
Visakhapatnam. Sir, one good news is our chairman sir also appreciating this FTP because for the last 2 days he's interviewing the best teacher awardees.
Okay, sir.
So
Yes, sir.
most of the awardees are also the participants of this FTP program.
Very nice. Very
He
nice.
straight away asked the participants about this faculty development program, how is it is going on, and the feedback received by him is very well, sir.
Right.
And just now he told that many of our faculty they are getting 19 out of 20 in the quiz.
Right.
That
sir.
shows their commitment and very good teachers are dealing with this. And
Right.
everybody is impressed. Even the non-mathematics fellow is also now doing the linear algebra like this. So he has so much of appreciation for the EACT and your team, sir.
Yes, sir. Thank you, sir.
Because he interviewed almost 50 to 56 members, professors.
Right, sir.
Most of the professors they have enrolled in this FDP program.
Right. Right.
So this is also one good feedback on this FDP.
Yes, sir. Live feedback. Yes, sir. That's good.
Thank
Actually,
you so much, sir. Thank you.
yeah.
All
Teachers are
all
putting a
your
lot of
team.
effort. I can see, ma'am was not, I mean, some personal family situation was there, but today she still was there on time to take the lecture. So
Yes.
I can really appreciate that. It's a teamwork, and
Yes, sir.
thank you, sir. Yes, and then yes, slowly the confidence will build, and I think they will be more comfortable. And I could see, sir, Anil sir shared somebody is making spiral mind of the slides
Yes,
and
yes.
reading and taking notes. I was really surprised. And of course, AP people commitment, everybody appreciates that you are very much serious. So I think our state will benefit a lot from the efforts that are going on. So hopefully, please continue the same hard work. And it's a long journey. We have till March. We'll complete all the 10 courses. So please continue the same interest and rigor, right? Thank you. Thank you. Thank you, Anil sir. Thank you for the
Thank you.
feedback.
Thank you, sir. Thank you.
Right, sir. Okay, sir. Right.
Thank you, everyone. Thank you.